Welcome and thank you for joining our webinar, Robust MPC for Uncertain Parameters. I'm Misha Saint-Amand. I'm the head of marketing for JuliaHub. And today I'm joined by our presenter, Dr. Fredrik Bagier-Carlson, who is the lead of the JuliaSim control systems team at JuliaHub. A little background, he holds a PhD in automatic control from Lund University and has 10 years experience in the fields of modeling, control, system identification, and robotics. Well, it's a pleasure to welcome you to the webinar today. And Fredrik, I'll let you get things started.
Thank you, Misha. All right, welcome everybody to today's webinar. The topic for today is model predictive control. It's very exciting. And today we're going to talk about how we can use MPC to control systems where we have some uncertainty and do that in a robust way. But first, we're going to talk about JuliaSim, which is the platform in which we develop these tools. JuliaSim is a suite of modeling and simulation tools. It's built on top of the JuliaHub platform. It's a cloud-native platform where you can run batch jobs in parallel, collaborate with your collaborators, and all of these interesting things. JuliaSim control library, it specializes in things like model predictive control, which is a model-based advanced control functionality. We also have things like optimization-based tuning, which you can see in some of our other webinars. We also integrate with the modeling language modeling toolkit, and we also have integration with our other products. For instance, JuliaSim model optimizer for optimization-based calibration of parameters and things like JuliaSim neural surrogates. If you have a complicated simulation model that is slow to run, you can build what's called a neural surrogate, which is hopefully much faster, but maintaining the accuracy. But today, we're going to talk about robust model predictive control. And there are a few words in this title. We'll try to break them down before we start. So first of all, what is model predictive control, or I would say MPC very often? It's an advanced control technology that has been around for quite a while, but it hasn't traditionally been used all that much in most industries. And the reason is that it has traditionally been very computationally intensive. And what you do is you use a prediction model. So that's a dynamical model of your system. For instance, in the most basic case, it's a transfer function or a linear state space model, but it can also be a nonlinear model, perhaps implemented in modeling toolkit. You use this model to predict or simulate forward in time. And then you solve an optimization problem. So you optimize your future actions so that the simulation optimizes some kind of cost function. Perhaps you want to maximize profit, or you want to minimize some error or something like that. And then you close the loop by doing this repeatedly over and over and over again, each time you get a new measurement. When you get a new measurement, your belief about the world, the state of the world changes, and you solve the same optimization problem one more time, and you update your plan of action. So that's a model predictive control in a nutshell. And what is an uncertain system? Very often, or actually all the time in control, we deal with uncertainty. Perhaps our system model is not perfect. In fact, it almost never is, right? Maybe we have some uncertain parameters, and that's what we will talk about today. But we can also have things like uncertain dynamics. Maybe we forgot to model some part of the complicated dynamics that govern the system. Maybe we are just not aware of any good equations that describe our system. Maybe we have some uncertainty in the measurements. We have measurement noise. Maybe there is some uncertain disturbances affecting the system, and so on. We can have lots of sources of uncertainty. But today, when we say uncertain systems, we will talk about parametric uncertainty. So we have some uncertainty in some parameter that belongs to the system. So a robust MPC controller is a controller that performs reasonably well despite the fact that we have uncertainty in the model that is used for the MPC controller. So we have an example here. It's a very simple example. It's an integrator. So P of S here, it's a transfer function, K, times 1 over S. And 1 over S is just a Laplace transform of an integrator. But we have some uncertainty about the parameter K, the gain here. It can be either 0.5 or 1 or 5. All right. So in the plot here, we have simulated for about 4 time steps. And then if we predict forward in time, we see we have 3 different prediction in dashed lines here. And these three predictions correspond to the three different possible values of the parameter k. We also have a little constraint here in the bottom that this x, the state, is not allowed to go below, I don't know what it's, 0.1 maybe, sorry, negative 0.1. So we must make sure that no matter what the parameter value of k is, we absolutely don't violate this constraint. All right, but subject to that, we want to maximize or minimize some loss function. And perhaps we want to minimize the average of these three, the loss of the average of these three simulations, or the worst case or something like that. I think in this case, we have minimized the average. And then we close the loop by doing the simulation repeatedly. So here we show an animation of how that can look. So we simulate one step at a time, solve the optimization problem. We have different predictions going forward in time. But the critical point here is that we make sure that we satisfy the constraints for each potential realization of the system. So this is one version of a robust model predictive controller, and that's the one we will talk about today. There are several other definitions of a robust MPC controller. We have some of them implemented in JuliaSim control, if you're interested. But for today, we talk about this particular version. All right, so why do we want to use MPC in the first case? And there are a few different reasons why MPC is an attractive control technique. The first one is that it very naturally handles multiple input, multiple output systems. So many of you are perhaps familiar with the standard control methodologies like the PID controller, and they are inherently single input, single output. You can, depending on the situation, extend them to MIMO systems, but it's not entirely straightforward to do that. MPC, on the other hand, is naturally fits MIMO systems. But the most interesting reason we use MPC is really that it allows us to handle constraints in a principled way. So constraints can apply to any of the variables in a control problem. Very often it applies to inputs. In fact, it pretty much always applies to inputs, even if we sometimes ignore that. If we have a motor, we don't have infinite torque capabilities. We never have infinite acceleration capabilities, and so on. We can never run a compressor more than for full power. If we try to run it harder, it burns up perhaps. So that's a constraint that is always present, but we can also have constraints on the state variables or on the outputs of the system. Perhaps if we are moving a robot close to a wall, a constraint might be that we're not allowed to crash into the wall. That would obviously be undesirable. And the third reason we might want to use an MPC controller is that we can optimize things like economical objectives. So perhaps we want to maximize profit, and we can write down a mathematical expression for the profit. But then it's very natural to try to actually maximize that rather than trying to optimize some quadratic loss, such as for an LQR controller, because we do that not because we want to optimize a quadratic loss. We do it because it's easy. But with MPC, we don't have such constraints. All right. So to get started here, I'm loading a bunch of packages. I obviously load the JuliaSim control package. And this is available in the JuliaSim IDE on JuliaHub. You can actually try this for free by creating an account on JuliaHub. And you have access to the standard tier without providing any credit card information. And using the standard tier, you can access these packages for a few hours each month. I also load the JuliaSim control MPC submodule and then some utility packages, plotting and so on. The system we're going to control today is called a continuously stirred tank reactor. It's often abbreviated CSTR. And we see a little picture of the system here. It's a reactor where we have some kind of chemicals appearing inside. In this case, we have two chemicals, A and B. And the idea is that we want to make one of the chemicals react and turn into the other chemical. And when we do this, when this reaction from chemical A to chemical B takes place, it's exothermic, so it produces heat. And the tricky point of this system is that as it gets warmer, the reaction rate increases. So you can immediately see how that's an unstable system. You can run into something called thermal runaway, where the reaction takes place, it gets hotter, the reaction gets faster, it gets even hotter, and so on until it gets out of hand. But to counteract that, we have a cooling jacket where we can send in a cold fluid to regulate the control here. We also have another control signal, which is the feed rate of a reactant A. So how much we feed in of the first chemical that is being reacted into the second chemical. All right, so we have 2 control inputs and we have 4 state variables, the 2 concentrations and the 2 temperatures. We have some equations of the system here. We're not going to dive deep into these equations, but we see that they are highly nonlinear. We have some exponential terms with state variables appearing in the exponent. We have some absolute value square and so on. So this is a nonlinear, rather a complicated system. But that's not the problem for model predictive control. We can easily solve nonlinear such problems also. So we start out by defining some parameters. Here we just defined some variables for the number of control inputs, the number of states, and a sample rate, an initial condition here, initial state. And here we specify a reference vector. We don't care about most of the states. We only care about the concentration of the second reactant here. And n equal 20 is the MPC prediction horizon. That's for at each time step, we predict 20 time steps into the future and optimizes the trajectory of control inputs over a horizon of 20 time steps. We also define 2 scaling arrays. That's for numerical purposes. This is optional, but if we do that, the numerical performance of the solver improves slightly. So here we just give the rough magnitude of the states and the control inputs. All right, we also have some parameters defined. It's just a named tuple in this case with a lot of different parameters inside here with numerical values. And these you typically find in perhaps a scientific article that has created this model of this system. I said before that one particular attractive aspect of a model predictive controller is that we can have constraints. And in this case, we have constraints on the minimum and maximum values of the state variables and the minimum and maximum values of the control inputs. And I package these arrays into an object called bounds constraint. If we have more complicated constraints, we can have constraints on any arbitrary function of the state and the inputs. We could add such constraints also, but for this system, it's not required. The next step is to define the cost function. So this is what we actually want to optimize with the MPC controller. And in this case, we want to optimize the squared distance. So abs2 is absolute value squared between the second state and the reference for the second state. So this is the concentration of the second reactant. And I put that inside a stage cost, which means that we compute this for each time step over the simulation horizon. We also define something called a difference cost. So that is a convenience function that allows us to penalize the difference between a variable in 2 consecutive time steps. And it's very common in MPC to penalize the difference in the control input rather than the absolute magnitude of the control input. So here I have a little function called getter. It takes the stage input and it produces a vector with the first and second control outputs. And I penalize the absolute value squared of those differences. And we can also have a terminal cost if we want that penalizes the terminal state in each simulation horizon. And in this case, it's just identical to the stage cost. We can also add things like a terminal constraint that would enforce that we end up inside the terminal constraint set, which is sometimes beneficial for stability purposes. But in this case, it's not required. So I've defined 3 cost elements here. I package them all into this type called an objective. So that's the objective of the optimization problem. And next, I provide an initial guess for the trajectory. And in this case, I just create a random vector here. And this initial guess for the state reactor is just the initial condition x0 repeated. Because in this case, the optimizer will happily find an optimal solution with a random initial guess. But for some problems, it might be a very non-convex optimization problem, and it might be hard to find a good initial solution. And then you can provide a better initial guess here. But for this system, it's not required. Next, we define a solver. And here I use the IP-opt solver, which is an open source interior point solver, which is a good general purpose solver. It's typically not the optimal choice for MPC. But if you have access to any other solver, you can make use of that as well. And we support any solver that is supported by the optimization.jl package. So you can use things like global optimization solvers. We have a few examples where we actually make use of mixed integer solvers. If you have integer control inputs, that can be beneficial. But for today, we can make use of the IP-opt solver. I also specify what observer I want to use. So the observer is the state estimator that takes the outputs, the measurements of the system, and produces an estimate of the current state. And in this case, I use full state feedback. So that just means that I have access to the full state. But oftentimes we do not have access to the full state, and then we can use maybe a Kalman filter or an extended Kalman filter, unscented Kalman filter, something like that. There are several different options. All right, the last step is to define a discretization. So our dynamics is describing the system in continuous time. So the derivative of the system, the time derivative of the system, is a function of the current state and inputs. But to find an optimal solution, we need to discretize that so that we have a finite number of optimization variables. And the MPC package supports a lot of different methods of doing this. Here we use collocation on finite elements, but you can also use some Runge-Kutta method, or perhaps a trapezoidal integration or something like that. But collocation on finite elements is a good default choice. All right. Now we have specified a lot of different objects, and we package them all into this struct that is called a generic MPC problem. And I call it generic because we also have a quadratic MPC problem. If you have, for instance, want to use linear MPC with a linear prediction model and a quadratic cost, then we call it a quadratic MPC problem. So here I just list all the things I've created previously. All right, so we can solve it. I just call mpc.solve, and I specify for how long I want to simulate, and then I create the plot. And we see here the first 4 plots are the state variables, and the second 2 plots are the control inputs. And we see here that the concentration of reactant B, it starts at some initial state here, and then it goes up to the reference in dashed here. So that's very non-dramatic. It looks all right, right? Maybe that's what we would like to see. And we see we have some dashed lines in these 2 plots in the middle corresponding to constraints, and we satisfy those constraints. So that's very non-dramatic, and it works the way we would expect. But now comes the interesting part here. Now we introduce some uncertainty. So here I have introduced a 5% error in the parameter that corresponds to the activation energy. And that's the energy that is released when the reaction takes place. So what I do here is I take the parameter named tuple from before. I then set the index here, so I change this particular parameter, and I lower it by 5%. All right, and then I solve the problem again. And now we see that we have an initial transient here where we approach the reference, but then after a while we violate the constraints, and the controller completely freaks out, and we violate, in fact, it doesn't even recover. So here we have experienced thermal runaway. So now the tank reactor is much hotter than the constraints that we had specified. And that's because we were not entirely sure about our system model. The parameter we had specified in the MPC controller was not exactly the real parameter that the true system had. And this obviously makes us quite concerned that maybe we do not want to put this controller on on a real tank reactor. But how can we mitigate this? How can we make ourselves robust to that uncertainty? And the solution is to model the fact that we are uncertain about this parameter and tell that to the MPC controller. And that's what we will do here. So here we will model a plus minus 6% uncertainty in this activation energy. And I do that here. I create an object called MPC parameters. Here is the nominal case, it's just P. And here are two additional cases. One case where I lower it by 6% and one case where I increase it by 6%. And then I create a generic MPC problem in exactly the same way. And I also specify that my robust horizon is equal to 1. You can think of this as activating the robust MPC controller. And then I solve the problem again. And this time we have a little animation here. And now we see that instead of producing a single simulation forward in time, we always produce 3 simulations forward in time. And these 3 correspond to the 3 different potential values of this activation energy. And we also see an interesting phenomenon here, that we never actually reach the reference of the second concentration of the reactant B. We see that all 3 realizations of the parameter could reach the reference, but they never do. And the reason is that we can see the reason if we look at the control inputs. The control action we would take, depending on which realization of the parameter we have, varies quite a lot. For one of the realizations, we would here take a large increase in the control input F, whereas for the other 2 realizations, we should actually decrease F going forward. So what the controller does, it takes the safe middle ground and make sure that we actually satisfies all the constraints, because we don't, in fact, know the true value of this parameter. If we had implemented an adaptive MPC controller, we could actually try to learn the true value of this parameter, and then we could perhaps do better here. But in this case, we don't have an adaptive controller, we have a robust controller. So it does the safe thing and stays a bit away from the reference here. All right, and here we see the plot without any animation. And here we see this phenomena that we didn't actually reach the reference that we were looking for. But nevertheless, this was a very simple way to specify uncertainty in a system. In this case, we specified uncertainty in a single parameter. We are not limited to that. We can specify uncertainty in one or several parameters. The optimization problem underneath becomes a bit more expensive for each additional parameter we specify uncertainty for. But for a lot of interesting problems, we can still solve them in sufficiently fast to actually make use of this. All right, so we have some concluding remarks here. Today, we have defined a standard nonlinear MPC controller that optimizes the performance of a continuously stirred tank reactor. Then we introduced some uncertainty in some of the parameters, and we saw that the system actually got unstable. The controller was not able to stabilize this system with a model uncertainty. And then we defined a robust nonlinear MPC controller that was aware of the uncertainty and tried to do its best to optimize the performance subject to satisfying all the constraints given the model uncertainty. All right. Before we end here, I would like to speak a bit about additional resources. We actually have a lot of additional resources that you reach if you go to help.juliahub.com. And we will have a look at how that can look right here. The webinar for today, you reach it by going to help.juliahub.com, pressing JuliaSim, and then you press Control here. And that takes you to the front page of the control documentation. Here you can read about some introduction, some background, how JuliaSim control fits into the wider ecosystem for control design analysis in Julia. If you go to tutorial, we have a large number of control tutorials here, spanning from linear tutorials using modeling toolkit, optimal control, and MPC. And under MPC, we have a large number of tutorials here as well. The tutorial we went through today is, you find it here, controlling a continuously stirred tag reactor. And here you see the entire webinar I went through today, if you want to follow along in your own pace. I should mention again that if you create a free account on JuliaHub, you can actually run this code in the JuliaSim IDE if you want to try it out. All right, and that more or less concludes my presentation for today. And I would be happy to take any questions. You can type in the question and answer box here on Zoom. I see that we have a question about the computational requirements. And the question is whether the computational time increases as 3 to the n, where n is the number of parameters for which you specify uncertainty. So that depends on exactly how many realizations of the parameter you specify, and if you choose a grid for the uncertain parameters, or if you do some smarter sampling. If you do the naive sampling, say that you have 2 parameters and 3 realizations of each, then indeed you will have 9 realizations. So you would have a number of variables in the optimization problem that scales the way you mentioned. But the time to solve the optimization problem doesn't actually scale as bad as the number of variables. And the reason is that several of these variables, several of these realizations often behave similarly. So the model predictive control problem doesn't become hard with the same scaling as the number of parameters. But yes, typically you do have an unfavorable scaling. So if you have a lot of different uncertain parameters, the problem becomes very hard to solve. However, we have a number of additional webinars we have held before, if you're interested, about creating what we call a model predictive control surrogate, or a neural predictive controller. And what that does is it uses modern machine learning techniques to replace the optimizer with a machine learning model. And then you can actually solve very computationally heavy MPC problems. And once you have trained this, perhaps in the cloud in parallel, you can actually compute the control signal extremely fast, easily in 1 megahertz. So there are ways to mitigate extreme computational expense. But nevertheless, for a small number of uncertain parameters, this is very feasible to actually run online with the optimizer as well. Thank you for your question. Do we have any additional questions?
Give folks just one more minute to type things in.
Yeah.
I think that might be all for today.
All right. Then I wish you all a happy rest of the day, and I say thank you for attending the webinar. Thank you, Misha.
Thank you, Frederick, and thank you for attending. We will be following up with an email with a recording, as well as links to all the resources that Frederick mentioned today. We look forward to seeing you at another webinar soon. Bye.
Bye.